Hi, everybody. You're going to need your book, pages 103 to 106 for these notes. So please make sure you have those. It just makes it easier to sort of follow along. We're going to go through today composition, and we're going to go through it in a lot of different ways. We're going to go through some things you've not seen before with absolute value and graphing. We're also going to go and talk about things that you do know, like domain and range. So we're going to use domain and range for this first story problem. And the idea is if you can kind of understand the meaning, then you might be able to sort of backwards think or think in reverse direction to get to the solution that you're looking for. Let me show you what I mean. So we've got this hiker and in the national park is missing, and the search and rescue team estimates that the hiker would have been walking at a rate of 2 miles an hour. The rescue team needs to determine the possible search area in which to look for the hiker. The theoretical search area is circular. Write the equation of a function f of x that gives the number of square miles in the search area when the radius is x. Well, this is just the area of your circle. They're telling us to use f of x. Area of a circle is pi r squared, but we're going to use pi x squared. Hope you enjoyed the bell. So before we go any further, I'm going to kind of let's force ourselves to sort of think through this. What is the domain and what is the range? What are we putting in and what are we getting out? Again, just in hopes that if we make some sense of it as we go, it'll be easier to put it together. We're putting in miles, right? So radius is x miles, so the domain is in miles. The answer we're going to get out is the area. And so if we're putting in miles, the area of our search area would be in miles squared. Now they want us to write a new function, g of x, that gives the distance in miles that the hiker could have walked in x hours at a rate. So now we're throwing in rate, and we know that distance equals rate times time. So we're supposed to use x, and so if we're going to 2 miles an hour, that's our rate, and our time is x. So 2x. Now let's talk about the domain here. Here the x value is hours. We're putting in hours, but the range, the output that we're getting is miles, because that's the distance. So we have some similarities, we have some differences in our two functions. So we've already done adding, subtracting, multiply. Today we're going to do composition. And composition is explained with that open circle, f of g of x. And that's how it's written. You might see parentheses around the f of g, you might not. This is the same thing as f of g of x. I feel like this notation is a little bit more descriptive because you can physically see that the g is inside the f, but they are interchangeable and expect to see both notations. So now you've done this before, and we're going to do one with our two functions now because they want us to write the composition of f of g of x. So we're going to take g, which is 2x, we're going to take this function, and we're going to plug it into here. Now, when you use substitution, which is what we're doing, you better use parentheses because it changes the meaning. So we have this pi, right, because f is our function, and then we have to do x squared. So we have to do something squared, and our something is the g of x. So we'll put this 2x in here. Let's just simplify this a little bit, and it's 4x squared times pi, and I'm just going to write it that way, 4x squared pi. So let's kind of go back through now and sort of decide, well, what's happening? What are we putting in? What are we getting out? Let's look at this in terms of domain and range. It's asking you a question, what does it represent in the situation? But I just want to go through and kind of explain domain and range since we have it all spelled out. So to answer the question, what does the input of the composition represent? So we're putting in hours, right? That's what we're putting in. Right, because the reason is this is the domain of g of x. We start with g of x. But let's go through, I want to break this down a little bit better. So if we think about g of x, the domain we said was hours, and the range is miles. Just going back through what we said, and then if we think of f of x, I started with g of x because that's what you start with when you do composition. Our domain here is miles, and our range is miles squared. And the way this works, now that we have kind of words, maybe it's a little bit easier to understand. When you take and you put g of x into f of x, these basically kind of cancel each other out. That's why we can use substitution there, because it's the output of one equals the input of the next. So then when we do the composition, we're putting in hours and we're getting out miles squared. So the domain is hours and the range is miles squared, which makes a little bit more sense to our problem that we're facing with the search team. I'm not going to do all the questions here. Number 6, what's the reasonable domain for the function? Because we've gone through and thought about the meaning, the reasonable domain for the function would be x is greater than or equal to 0, because it's time. You can't really say, we can talk about time in the past. We can say it was 2 hours ago, but we're not going to be able to say, oh, that's a negative 2 hours. So we want it to be greater than or equal to 0. For number 7, they want to use the distance in miles a hiker could have walked, which makes sense. So if I want to figure out the distance, so that's how we can figure out the search, we says explain why the composition is a good model for the rescue team to use. It's because you can put in the hours, all right, that was our domain, to find the area. We don't have to know anything other than how long has this person been missing, and now I can really say, well, now we need to search this many square miles. Well, of course, now they're going to have you figure that out. So for number 8, it says that they were last seen walking away 6 hours ago. Well, we already have the function written, right? It was on the other side. It was 4x squared pi, so I'm going to have 4 6 squared times pi. I throw that in the calculator. We'll go to 2 decimal places because pi is usually 2 decimal places. So then we have 452.39 miles squared, using correct units, of course. Now, of course, if we can go f of g of x, they're going to have us go the other direction. So now we're going to do g of f of x. It says use the equations you wrote to find these. I'm going to go back. F of x is pi x squared, and g of x, just in case you've forgotten, is 2x. Now, when we want to do g of f of x, that means we're going to start with this one, and we're going to put all that right here. So when we're going to write this as g of f of x, and we're going to end up with, well, this comes out. Substitution isn't, we really don't need to use parentheses, but you should just get in the habit of that. So we end up with 2 pi x squared on the inside. This is a different function than the other direction. So for number 10, this is an important thing to know. Is f of g of x the same as g of f of x? Well, that's a no. So what does this tell you about commutative? It's not commutative. Order matters, basically. So it's important that you do it, the composition, in the correct order, the order that you're asked for. Now we're going to get into some things that maybe you've not seen before. We're going to manipulate this graph. This is a big kind of idea in calculus. We do a lot of things with manipulating graphs in calculus, and so this is sort of a beginning of that. We're not going to do all these. I'm not going to do C, D, E, or F. Now the idea is, just from looking at your calculator, you can see a pattern. So they're asking you to take and put x to the third in the calculator, and then if we think of what this looks like as absolute value, it says that g of x is equal to the absolute value of x. So we want to graph f of x, the one they gave us, and g of x. So if you want to put this in your calculator, take a look at these graphs. See if you can find a pattern. For part B, g of x would then be, of course, the absolute value of x squared minus 4. Oops, that's an absolute value bar. Now, if you're not sure where absolute value is on your calculator, this is kind of a way to kind of do two things at once. You go to, obviously go to y equals, start there, then you go to math, and then you can go over to NUM, the math key, that third one down on the left, over to NUM, and then you'll see ABS for absolute value. But you have to start in the y equals menu in order to get that. And they want you to say, what is the pattern of this? Describe the effects of the absolute value transformation. And this is kind of tricky, so I'm just going to go through it the transformation is that negative y values. Think about absolute value. You don't come out with a negative answer. So it's only the negative y values that turn into positive y values. So describe this with the graphing. We'll say reflect over the x-axis. And this right here is something that you'll be expected to do with a graph that you cannot put in the calculator. So that's how we'll ask you to do this to prove that you understand the pattern. Is something that the calculator is not going to help you with, which we'll get to here in a second. So just like we did down the other ones, I'm not going to do, we're just going to do these. I like the natural log graph. We do a lot with the natural log in calculus, so it's an important one. You can do others if you'd like. I'm just going to graph those two myself, but you can graph, obviously, any of the other ones you want to see. This one, e to the x and the square root of x, those are pretty interesting graphs to graph and take a look at. But again, we're just doing this to look for a pattern. So for part A, if we think about what g of x, how would we write the absolute value of this? So g of x is the absolute value. We want just the absolute value of x. So just the absolute value of x with the power of 3 on the outside. For part B, this would be g of x. We just want the absolute value of x would be natural log, and then absolute value in x. So we have absolute value of the whole function, or just absolute value of x. This is a tricky transformation and maybe one that is hard to describe. So let me do my best to sort of make this concise. To the right of the y-axis is unchanged. So anything to the right of the y-axis, that graph stays the way it is. Left of the y-axis is eliminated. It's not there. So if you had anything to the left of the y, it's just gone. Like you just ignore that part of the graph, and it's replaced with the right side reflected. Maybe my directions and my descriptions aren't super awesome, but we're going to go through some and actually put this into life here, which is what we're going to do now. So we're just doing composition of different functions with absolute value. And now, because this is something that you have to sort of be able to think through, we're going to do this without the calculator. So we have a function on the right here, and I'm not really a super fan of this function. I feel like they did a poor job graphing it. I'm going to call this down 1 for sure. I'm also going to call this point, I'm going to call that -2, -1. I don't like how inexact they are. It's going to be hard to sort of graph, so we're going to basically sort of put that segment right there. It's ambiguous in the book, but we're going to use those exact points. So we're going to use 0, -1, and we're going to use -2, -1. The other points are perfect, so we're going to leave those alone. So let's take a look at part A. So here we're going to do g of f of x, where we're combining, where the absolute value, and this is the part that matters, the absolute value is on the outside, which is how the first one was. This is the absolute value of the whole function. So negative y values are reflected over the x-axis. So for this one, we can have no negative y values. So I'm going to start way over here at 4. So I'm going to start with something that's easy. Then we have 2, 1, because these aren't negative y values. And then we get to 1. Everything else has a negative y value, and so that has to be reflected over the x-axis. So this x-intercept is important. It's like the graph breaks here and is now going to be flipped over. So instead of going down 1, we're going to go up 1. And my point -2, -1 is going to turn into -2, +1. And this other point is -4, -3, which is going to turn into -4, +3. You don't change the values, you just change the signs. And so that's what this graph would look like. This is horizontal. Without graph paper, it's not quite as awesome. So for part B, and I'm going to write on my graph, The right side of the y-axis is unchanged. The left side is eliminated. This side, gone. She gone. And it's replaced with the right side reflected. So we're going to take this and we're going to reflect it over here. All right, so again, 1, 2, 3, 4. And then we have 2, 1. And I'm calling this negative 1, 0. All right, so this. You go right up to the y-axis. So it's like stuck to the y-axis, and then this whole thing is flipped over. So I'm going to go over 4 this way, and I'm going to go negative 2, positive 1, and it's just going to turn into that graph. Super weird concept. So this is the absolute value of the whole graph. This is just the absolute value of just the letter X. Order matters. The last thing we're going to do is decomposition. We're going to work backwards. So I'm all the way down at the bottom of page 106. I skipped the top of page 106. And we're going to take this, and it says, here's your answer. Your answer is h of x. And we want h of x, and we want to break it down. We want to go backwards into the two parts. And the inside is the g of x. So when we read this, when we read like 1/2 x minus 5, I'm going to think of this as something, anywhere the x is, minus 5, or something divided by 2, or whatever, wherever the x is going to be my something. The something is the inside function, whatever that is, and the rest of it is the outside. So our inside function is g of x. So for part A, I'm going to start with, okay, something minus 5. So f of x, the outside function, is something minus 5. And then my g of x, which is the inside function, or my something, is going to be the 1/2 x. That's just part A. So let's try this again. For part B, f of x, g of x. It doesn't matter what order you want. You want to start with the something, start there. So I have 1 over something. 1 over something. And then my something is going to be x squared plus 3. Not too bad. For part C, ooh, tricky. F of x, g of x. It's going to be 2 to some power, 2 to some power. And my power, which is my something, or my g of x, is going to be x plus 1. Now for D, there's always something going on here. We got to factor this. I got too many somethings. I got x in more than one spot, and I can't have that when I'm doing a composition. So I'm going to factor this out, x plus 3 on x plus 3. 3 times 3 is 9, 3 plus 3 is 6, all the signs are plus. So this is essentially x plus 3 quantity squared, or something squared. Haha. That's how we get around that. So if you have the letter x written more than once, try to rewrite your function as something else. Factoring obviously is usually good. So we have something squared, and the something is x plus 3. Don't forget to do your assignment, and have a nice day.